Stuff is happening, things are happening, stuff and things are being done. There is an exam on Friday. How is the preparation for that going? Anything I can answer before our official study period on Thursday? I guess that's another announcement, as we will be having a study period for it on Thursday. So please come with questions. I revealed the last required assignment. I put it due a week from Friday. Do note that there is that optional assignment as well that will be coming as soon as we get to the relevant content. That will also be due that Friday. So if you're thinking that you would like to be able to do that optional assignment to drop a lower score, then you will want to get started on that sooner rather than later, because another assignment will be coming with that same due date. I just wanted to give you as much time as possible for submitting both of those, but plan ahead. The plan for the rest of this week is to finish off this heap. I would also like to start talking about graphs. Then whatever time is left over next week, I want to talk about interviewing, because that is a very important topic in this field that there's just no curriculum for. So I've tried to hold a pace throughout the quarter that will let us get to that, so that you know what you can be doing to prepare for when you want to be interviewing. Some of you are doing it right now, some of you have landed internships for the summer. That's awesome. Even if you're thinking, I'm not going to do anything until I graduate and want to then start interviewing, there is work and preparation you can be doing now. And what just things you should be thinking about as you go through your courses to organize, to prepare yourself for that process. So that is what we will talk about with whatever time is left over. Hopefully there's enough to really be meaningful. Questions before we dive back into our heap? I feel like that has at least a couple of meetings. All right, so we wrote our fields, our constructor, our basic size and is empty methods. We wrote an insert, and as part of insert, we need to write heapify up, because insert is going to put an element in the last position in the underlying array, which violates some heap properties. So we needed to write heapify up to be able to restore those heap properties. So we did that. We just have to write the swap. So let's go ahead and write the swap. So note that we're not taking in a list or anything of the sort. It's because that we're intending we're going to use this array of elements as our swap. What do we want to call this? Any suggestions? What do we want to call the two things we are swapping? We don't want to call them current index and parent index, so that would always be the case. Sure. We'll use some generic names. That seems fine. All right, there's a nice easy swap for us. Now our red squiggly under the swap goes away and we have that implemented. I made it private just because the end user should not be calling swap on our underlying heap. They're probably going to mess something up. If a client can mess something up, they will mess something up. Don't give them that power. More of that to come in 350. Okay, so we did insert. Let's start to tackle remove. So maybe someone can quickly summarize the remove algorithm. What is it that at a high level, not necessarily code, what are we looking to do in remove? That was a wonderful drawing. I agree. Yeah,
We'll have the only element we can remove from a max heap is the largest element.
yeah,
It might be different than what we're doing up here, but
it's about the same thing. Where's the smallest element going to be in a min heap? At the root. Exactly like where the maximum element would be in a max heap. The minimum element would be at the root, and we can only remove the minimum element.
no, we'll delete the root. Right?
Yeah, we're gonna swap it with the last element. Delete what used to be there, and then we're gonna call heapify down as we now swap that with its largest child all the way down until we don't need to do that anymore. Yeah. So let's go ahead and write that. Since remove returns the element that was removed, that's just across any collection in Java, that's a standard behavior. We're going to return that. Remove doesn't take any parameters because we know right where we're gonna find it. There's nothing that the user needs to do with this. We should probably throw one kind of exception. If we try to remove from an empty heap, that should not work. All right, once we're done with that, what we have is if statement. Just throw this in the next. See it. After we do this, then we want to remove, we want to swap with that. So let's first say that we're going to store off the root. Call it the root, that's what it is. And it's stored at position 0 in the array. We have to be careful of knowing that this is in an array and not in an actual tree structure. So the root is at position 0 in the array. So after we do that, we want to swap that element with the last element in the array. So we can just call swap, and what do we want to swap? Yeah.
0 and size -1.
Yeah, size -1. Be careful of doing something like the size of the array -1, because we don't know that the array is filled all the way. So size is this field size that is keeping track of the number of elements that are in our heap. So that's the same size that we bumped up when we inserted. We're just keeping track of the number of elements that are stored in the heap. We know the last element in the heap is going to be at position size -1. We want to swap the first element with the last element. And we can easily do that because we know the indices for those based on the size of the array, or based on the number of elements in the array, size of our heap. Excellent, so we're swapping to do that. Then we can basically just set what used to be the root that we swapped to the very end to null. So let's go ahead and do that. This effectively deletes it from the array. As we delete it, we should do something with the size. We decremented it, so we should decrement the size. And we're ready to call heapify down. And we can just return what we removed, the root. Questions on remove? This is the entirety of remove with the logic of heapify down abstracted into something that we will implement next. No further questions? Yeah,
What's the point of having your functions like by down and like things by up if they're not going to be public to be removed? Like, why not just write it in the room?
because there might be other things that we do to it that cause us to need to bubble something to the top or bubble something down. It also would make these methods a little bit on the long side.
Yeah.
So I'm future proofing a little bit by thinking, all right, this is a portion of this method that is reusable and may be factored out or may want to be factored out in the future if we want to do anything else that does that behavior. And it's the most relevant part of that, aside from swap, to factor out from remove. It makes all these methods nice and short. And I find that fewer bugs are introduced if you try to discretize the logic down into smaller and smaller components. It's harder to make mistakes if you're thinking about smaller chunks rather than how do I make a heap? That is a large question that is difficult to answer without breaking it down into more abstract steps. All right, heapify down. Let's actually write it as private because we certainly do not want this being called randomly. So heapify down. How do we want to start this? Yeah,
Do we want to start by swapping, or I guess we go to swap.
yeah. What are we gonna need to keep track of as we do this?
The parent index, so starting at the root. And then
Yeah.
the child indices.
Yeah, we need to keep track of two nodes as we go down because we're gonna need to be comparing largest child, smallest child, swapping with that, and then keeping track of where we came from as we do that. So let's start out a parent index. I like that name. We'll set that as the root at index 0 for the moment. Let's also figure out where this node's left child and right child are, because we're gonna need to compare those things. So let's figure out the index of the left child. Where did we say the left child is compared to this node? What was that expression we came up with?
Index.
Yeah, so 2 times the parent index plus 1. And the right child is going to be found at index 2 times the parent index plus 2. Great. We need to now figure out of these, which one is we said that the largest child for a max heap. Is it gonna be the largest child or the smallest child for a min heap? Does that change too, or does it stay the same? Yeah,
Quick question, is the root of the min being the smallest number and then the left going.
Yeah.
Okay.
yeah,
Why do you have two children?
yeah, so this is in the array, this is where the left child and right child are gonna be located. A couple class periods ago, I drew out kind of the tree-based structure and the array-based structure, and then asked, all right, assuming that we're at this particular node, where do we find the left child, where do we find the right child, where do we find the parent? And we derived some formulas for that. These are just those formulas based on the location of the current. So we borrowed that from our work from a couple class periods ago. Yes,
So assuming that our roots are minimum, when we have to let them right, see what it is.
Yeah, it is smaller, not larger, because we want to swap with the smaller element, not the larger element. If we move the smaller element up into this position, then it's gonna be a true min heap for the other child as well. It'll still be larger than that child, sorry, smaller than that child, and that is legal in a min heap. So that's exactly what we want to do. In fact, we're gonna factor this out as well into another method. So we're going to call this select smallest child. And we're going to pass in the left child and the right child and tell us which one is smaller. When we do this, it's gonna return something to us. We're gonna store that as an int. So we want to pause this and write that real quick, or do we want to continue this process, assuming that we have the index of the smallest child stored in smallest child? Yeah, we're comparing a method call to something we haven't written yet. Yeah, it's a call to that method, so we're gonna write it outside of the scope of this method eventually.
Can we write the line first?
Yeah, let's write the method first so we just see how it's going. Sure. We'll pause heapify down for a moment and we're going to write select smallest child. We said this takes 2 integers. And we'll return an int. Okay, how are we gonna do this? So there may be some side cases to this. There's some things that we might want to consider. What do we know about what could be done here? So are left child and right child guaranteed to exist? What happens when we call select smallest child from a parent that their left child and right child are potentially null? What would that behavior look like? In the array-based structure, how could we identify that these children are potentially out of bounds?
Be size 1, size 0.
Can you compare the past and indices to the size?
Yes, that's exactly what we want to do. So either the size or the capacity, one of those would be a way of determining whether we don't even want to consider what's there because we don't know what's in that array at that position. It could be 0. It could be something that would look like, if it is 0, maybe that's what it looks like, the smallest child. That's not good. So we want to make absolutely sure of that. So we're going to quickly say if the left child is out of bounds. So we could, if the left child is greater than or equal to the capacity, or if the since this is a t, it wouldn't really be 0. The value that's stored there would actually be null. So if we look at the position of that left child, if that is null, that would be another example of something that is out of bounds. We would want to return some value that indicates failure. So you return, since this returns an int, you just return something that's not a legal index. And that way, we can easily see failure without throwing an exception necessarily. Throwing an exception is kind of a worst case. You don't really want to do that unless you have to. So if you can return a value that indicates failure as opposed to throwing an exception. Exceptions are really for exceptional behaviors if it's going to crash your program. But this is kind of the equivalent of that. And then instead of having to surround this with a try catch, then you can just check for if the value returned was -1. So if we do that, that's good. So if we get past this, what do we know? What can we do?
Yeah, we check the line file.
Yeah, we kind of, well, if the left child is no, then because of what we know about heaps, the right child also has to be. Because if there was an element there, it would be in the left child, not the right child. That's a very good thing to be thinking about for sure. But I think by the fact that we are making a heap, this does that by default. When would we want to return the left child?
We refer from.
Yeah, yeah, so the first thing I'm actually gonna check before we try to access elements of right child and compare it, because that could be null. It could be that the left value has a value and the right value does not. So we want to check and make sure of that first. So we're going to utilize that concept of short circuit evaluation to check something in an and or an or that would cause it to fail if it's going to be a value that's out of bounds. So the first thing we should write is if elements speak and type at the same time, if elements of the right child is null. That's the first time you just want to return the left child. But because we already checked here if elements of left child is null. So we know elements of left child is not null, it has a value. So because it has a value, if right child's value is null, we immediately want to return left child without dereferencing that. But now when we get past this, we can now dereference it safely because we checked for null on the left-hand side of an or. So that's that short circuit evaluation. So the right-hand side is we just need to make sure that the left child is actually the smallest of the two. At this position, we can assume that there are two. So we can check if elements of left child dot compare to elements of right child. What do we want this expression to be at this point? We want that compare to be less than 0, greater than 0. If we do greater than 0, that means that the value of the left child was greater than the value of the right child. Yeah, we want less than, in fact, we're even gonna break the tie. Break this down, make it visible. So if that's all the case, then we just return the left child. If that's not true, we can just return the right child. In fact, we don't even need an else. We can just, if we get this far, we return the right child. So here's our select smallest child. To be complete, should work. Question?
Why do we compare the left child index to the capacity instead of the size?
Yeah, this is to just say if it's out of bounds of the capacity of the array, if it's the size, we really could say size here. We'll go ahead and do that, why not? All right, now we have select smallest child implemented. Should be correct. We'll test this at the end to make absolutely sure. All right, once we get past the smallest child and heapify down, changing our exact question.
Real quick, could you explain one more time what like compared to doing like?
Yeah. Yeah, so the compare to is checking the value of elements of left child and comparing it to the value of elements of right child. So this is just our array of all of our values. We have our node and we have its two children. So we want to figure out which one of them is smaller and return the value of the smaller one. So if we compare both of them, we see that it's going to be less than 0 if this left element is less than or equal to this right element in here, which would identify that the left child is the smaller of two. So if this evaluates to true, then we want to return the left child as the smaller of those two elements. If that's not true, the only other thing is that the right child would be smaller than the left child, in which case we want to return the right child. So this is the equivalent of an else down here. It's just that in a method, when you return, you are done. So there's no reason to even write the else. An extra unnecessary line. Great question. Yeah,
Might be getting ahead of myself, but unless we're passing the parent index as a parameter, why are we doing math on something that's always just gonna be 1, 2?
for
2
right here.
plus 1.
Yeah, because we will be heapifying down potentially repeatedly. I think we will, that's a great point. And we're going to need to, we're gonna copy this as an element inside of a loop that we are about to write.
Gotcha.
Yeah,
That's why I
so
understand.
here we could hard code them.
Yeah.
As their values. Yeah. That is a good point. Yeah, we'll throw this up here now. All right, it's basically time for the loop. Once we've found the smallest child and we know where that is, we basically now need to repeat this logic a bunch of times. So we're gonna get into that. We can say while, but now we have a termination condition for this because we needed that smallest child to be able to know whether to terminate the loop or not, or even to go into this loop or not. So what about the smallest child do we want to compare here? What do we want to find? Yeah,
Want to confirm that the array at the parent index is still greater than the smallest child?
yeah. So we want, first, we want to check whether smallest child returned a positive value, because if it returned a negative value, then we know that this is a leaf. So we can say, well, smallest child is not equal to -1, that failure indicator from our method. And we want to make sure that the element in our array at the parent is so if it's larger, then we want to swap. So we want to compare this to the elements, I cannot type that today to save my life, of the smallest child. And again, what do we want to do here? What do we want this to be? Is it less than? Is it greater than? Greater than 0? It has to actually technically be larger in order for us to want to swap. I agree. Bring this down. That's because this is outside of that. Okay, so we have our loop condition. What is it that we want to do if we identify that the parent is actually larger than the child?
Swap, parent and child.
Yeah. So we want to swap smallest child with parent index. What's next? How do we prepare for the next path? Yeah,
This is just a small thing, but does it matter what order you put parent index and smallest child
in the compare to.
in the swap?
Oh, in here? No, no, it does not.
Gotcha.
Because when we go down to that swap or up to that swap, wherever it is we wrote this swap, there it is. You can see that we just put I and J, which just happen to be basically, the concept is triangulation. Is that imagine that these are at three different locations, and then you can either move the triangle clockwise or counterclockwise, and you still end up eventually swapping those elements. If everything is moving in that direction, you swap I and J regardless of whether you're turning that triangle clockwise or counterclockwise. So it does not matter which order you pass them into with a swap. Nor does it matter whether you pull temp from elements I or elements J, it just changes. You do J, then this needs to be J, this needs to be I, and this needs to be I. So lots of ways to implement it. There's no one right way there.
The smallest index that would equal the parent index,
Sorry?
where you have to set the smallest child equal to the. parent
Yeah,
index. So-
yeah, to prep for the next pass through the loop, we need to set the appropriate indices to start the next comparison. So when we pulled off this swap, what's now at the index smallest child was this old query node that we are heapifying down. So to continue to do this, smallest child now needs to be set to the new parent. That's now the new parent. So we set parent index equal to smallest child. That index. Now we're ready to query the new node, but we need the indices of the new two children in order to do that. So we can now copy these two lines. Because they will reset the left child and the right child with the new parent index, since this is now what used to be the smallest child. This will get the left child and right child of the new swapped location. Are people able to visualize that? Soon we want to draw that. So we don't even necessarily need values here. So this was originally our parent index, this was our left child, this was our right child. So we identified whichever one of these was smaller, because after we did this, we violated the heap in some capacity. Let's say we found that the left child was smaller, so we did that swap. When we do this swap, in order to prepare us for the next time, you can see that the new parent index that we want to compare to children is what used to be the smallest child. When we figured out that this was the smallest child, the left child was also the smallest child. So when we say parent index equals smallest child, we're just saying this is now the new parent index. We get rid of that. And then to calculate the new left child and right child, you use this index, this parent index, to figure out where this left child and right child are now. And now this is just a sub-problem, a very similar problem to the one we just solved. We're just down one level in the tree structure. But the indices that we're using are based on all of this being stored in the array that it's actually stored in. So there's a lot of abstraction when dealing with heaps. Because you're thinking about this, but you're implementing it in an array. Which is a bit of a challenge. Questions on that or why these lines do that logic? Okay, we can continue. Anything else we need to do in this loop?
Smallest child again.
Yep, we need to find the smallest child one more time. Because in order to loop back around, the smallest child has to be the new smallest child, not the old smallest child. Absolutely, so we can call. In fact, it's exactly this same line. So we'll just copy that right down here. And that will prepare us for the next pass through the loop.
Yeah, decrement the size.
Not in heapify down. When we're removing, I decremented the size right before calling heapify down. When we remove the element, but yes, so we definitely do need to make sure that we do decrement the size, but it is in our remove.
Okay.
That is the entirety of heapify down. Questions on that method? We're getting there. We're almost done-ish. So some other fun things that we should implement, we should probably write some kind of two-string. So that we can visualize it. So for a two-string, we're just going to. Let's see. Let's write this in a fun way. Since we're using a base array, we can use arrays.stream. Arrays.stream just prepares that as a stream. So we just pass it the name of what we're going to be doing, but that's not good enough by itself. That's not what we want. We want to filter it because we only want to show the elements that are actually in use. So make a stream of it, filter it to only display those that are non-null. So in this dot filter, you pass this. This is kind of like a for each, comparing each element to null and only saying add it to the filter if, but you can use the arrow here to do that. So element such that is the way that I would read that. Filter for elements such that that element is not null. Elements. So you can call this whatever you want. This actually doesn't need to be this is basically saying an element. So when you do a for each loop, it's like for elements in elements. You would use that as a for each loop, and that each of those elements, the element in elements would each be a t in the array of t's. So this is basically doing the equivalent of that. It's saying we're filtering everything in elements such that we're looking for individual elements of that are not null. And that's what gets added to this stream. And there's one last thing we need to do to this before we finish, and that is to what we call collect all those together in one package. So this is just dot collect. And I actually don't think we need any. No, we do need something. What goes in the this collect? We want. Something out of the collectors class. We have to no, we won't. Collectors dot to list will work. Collectors dot to list, and that takes. That itself has a two string. What's missing here? Yeah, this closes that there. And there's one. Yes, that does it. I think this will work. Little bit going on here, but this is just a line that gets you a collection from an array, basically. A collection from an array with a filter. So I will file that down there so that we can see exactly how that's being visualized, but this will work. Arrays.stream elements.filter for each of those elements that's not null, collect those in a list with a two string, pass that back as the string that is the two string for this array. Java has lines like this a lot. This dot that dot something else and parameters everywhere. But that will work. Unless I've done something horribly wrong. But this is the last thing I think we really need to implement. So let's go ahead and write a quick tester with the last few minutes of class. And then I can also show off heap sort. Assuming this works. So in main, we're going to make one of these objects. I called it a min heap. We're gonna take a min heap of integer. We'll call it heap. It takes a parameter. If we go back up to this, we said a capacity. So let's go ahead and pass in a reasonable capacity. Let's pass in a capacity of 1,000. Seems like a reasonable initial number of elements to store in a heap. So let's go ahead and insert some things into our heap. We could just, since we were eventually going to want to sort this, we don't want to put in something that's in order, but we could put in something that's in reverse order to see if it sorts it. Let's say I equals 10, I is greater than or equal to 1. Decrement each time. When we do this, we're just going to call our heaps dot insert. We'll pass in I. After we do this, let's check out our heap. So let's call our heaps toString. Once we do that, let's remove from the heap. Once we do that, let's print it out again and make sure that it removed the smallest element. Once we do that, let's just kind of stop there for the moment. We're going to implement heap sort after this, as soon as we check and see that this is working. So let's run our main, and we see 1, 2, 5, 4, 3, 9, 6, 10, 7, 8 is our heap. So 1 is smaller than 2 and 5, 2 is smaller than 4 and 3, 5 is smaller than 9 and 6, 4 is smaller than 10 and 7, 3 is smaller than 8. Good. That is a legal heap. Then when we remove, we get rid of the 1. 2 is smaller than 3 and 5, 3 is smaller than, yeah, I think that works too. So we'll come back and add to this a little bit after we write us a heap sort. So heap sort is actually going to be pretty short and sweet, given that we have a heap that works. So let's go ahead, and this should also be public because we want the user to be able to sort whatever they make. Since this is now a method that's going to be called on an object that we create, it should be static. Heap sort is just going to take, for the moment, we'll only use some integers. Let's say we're going to pass it an integer array. Fun. All right, so in heap sort, we should make the heap that's going to sort. So we call min heap, and this is going to be a type integer. We can pass it. Let's make a capacity that is the array dot length. Seems reasonable. We don't need more than that to just sort a single array. Once we're done with that, we're going to step through the array and add each of those elements to the heap. That'll get that done. When you have a nice array of objects, you can just write a nice for each loop. And that will not have you worrying about the size. When we do that, let's store off an index. that we're gonna start at, and then we want to basically say, while. If we're gonna sort based on this heap, all we have to do is, when we inserted all of these into the heap, they're now in the heaps order. So we should just now remove and replace, starting at the beginning, because it's a min heap. If it was a max heap, we had to start at the end, but since it's a min heap, we start at the beginning. So we just basically say, while the heap is not empty. We want to store. Where in the array, we stored off that index for that reason, that's gonna keep track of the position that we're gonna be storing it in. So array of index is going to get what we removed from the heap. This is why we pass back whatever we removed from the heap. It makes it very easy to do something like this. And the last thing we need to do is bump up the index. And if we do that, then we just keep adding to the next position in the array, next position in the array, next position in the array, until the heap is empty. And since we made the heap exactly the size we need to sort the array, there should be no further issues. This should be about as easy as we can implement it and test it. So if we go back to our main here, we can start to test that. Let's make something to test with. Let's just say this is, I have to call it something. Let's say, let's just do the numbers in reverse again. Just to make sure we can sort things. And we would just call heap sort on our list. This should keep everything in the list order, so we don't have to do anything else. It's just passing everything by reference. And then we just again print out. Raise.toString for our list and make sure it sorted it. Run that, and we see it is sorted. So this is another log linear sort. We would see that this is also very efficient on large sized arrays. Yeah,
For the heap sort, it always utilizes a min heap as the underlying.
you can use a max heap, but then you just start out index here, instead of being at 0, you would start it out at the list's size -1 and backfill rather than fill up from index 0. So I find it to be a little bit more intuitive to sort with a min heap, but you can absolutely make a max heap work. Yeah,
Can you explain like why it sorts it in like regular sort of order versus like you just make it into a found heap?
yeah.
Makes sense?
So imagine that, let's actually write out what it would take to insert the numbers 10 through 1 into a heap. We have 1 minute to do this. Think we can do it? Probably not, but we'll stay a couple minutes late. You need to get working, walking somewhere. Go ahead and start thinking about that. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 elements. And if we were inserting these into a heap, you would start with the first element. But eventually, this is going to fill the heap with 10 to 1 backwards, which was this first printed value here. That's what we got. So after this is done, we basically have 1, 2, 5, 4, 3, 9, 6. 10, 7, and 8. Is this a legal min heap? Yeah. So basically, we took this array that has 10 elements in it. 1, 2, 3, 4, 5, 6, 7, 8, 9, one more, 10. And in whatever order this is, if we're going to remove from this heap, we first remove the 1. We set index to be 0, which is going to point right there. So we just said this 1 goes right here. And the removal process is we're going to swap the 1 with the last element in the heap. So this 8 becomes a 1, this 1 becomes an 8. Then we're going to heapify the 8 down, so we're going to find the smallest child, swap the 8 with that smallest child, so this becomes the 8, this becomes the 2. Heapify down, find the smallest child, is 8 larger than that smallest child? Yes, so we swap them. So this becomes an 8, this becomes a 3. Heapify down, this 8 and this 1, those should also, well, actually we deleted the 1, so now we're good. So now we loop this process. Remove from the heap, we swap the 2 and the 7. Delete the 2, return it, put it in index 1. Heapify down. Repeating this over and over and over again, we will eventually fill this array with them in sorted order, even though what we added to the heap was in reverse sorted order. That's the array that we made with reverse sorted order. But with this process, we get something sorted, yeah.
So this works because it's a main. Right?
If it were a max heap, we would just start index out here.
Yeah.
Rather than, and backfill, rather than starting at the beginning and moving up, but everything else would work. All that changes is just a couple lines in our heap sort that says index equals 0, that would change to size -1. And then instead of index plus plus, you'd have index minus minus.
I was gonna be able to pick this.
Yes, it's trivial to make a reverse sorted list as well. So it's a nice, it's very nice. It uses the concept of a priority. And so it's very useful in a computer science application where you need to think of a priority. If you have network connections and you need to figure out which of these network connections need to be resolved first. I like to think of a game setting, like, you know, you're in your death situation of like service game. You want the server to respond very quickly to that, as opposed to someone else who's playing, who can deal with an extra millisecond or 2 ping time to get a response from the server. To prevent you from being in a dangerous death situation. We'll be back tomorrow with more stuff.